Hello, and welcome to today's webinar on using predictive technologies with compressed air, brought to you by Plant Services and Kaeser Compressors. I'm Christine Lefebvre-Grace, Managing Editor of Plant Services. First, let me express our appreciation to you for joining us today. This webinar is sponsored by Kaeser Compressors, a global force in compressed air system solutions committed to maintaining the highest quality standards and delivering products that are built for a lifetime. Before I introduce our speakers, there are a few housekeeping issues that I'd like to review. On your screen, you should have several primary sections. The upper left, or audio control section, allows you to adjust the volume of this presentation. Just hover over this section until you see the audio volume control and adjust the volume to your preference. In the largest section is where today's presentation slides will be displayed. Under the slide window, you'll see a chat section where you can chat live with fellow audience members. To the left, you'll find a question and answers box where you can type a question for the presenters at any time during today's webinar. We'll get to as many of those questions as we can during the Q&A session that follows the presentation. If we're not able to get to your question during the webinar, or if you have a question after the webinar has concluded, Neil, Timothy, and Kaeser will be able to answer these directly later, so ask away. The handout section at bottom left contains links to several resources, including the full set of speaker slides, plus multiple resources from Kaeser, including a brochure about the Sigma Air Manager 4.0. Finally, at the bottom of your screen, you should see icons for additional features. By hovering over each icon, information about the icon will be displayed. If you're having technical problems, you can type in your question or concern in the question and answers box, and one of our technical engineers will assist you. Need a better view? You can enlarge a section by clicking on the box in the top right corner of the section next to the X. If you accidentally close out of a section, you can get it back by clicking the Restore button. This webinar will be archived, and we encourage you to direct your coworkers to the recorded presentation. At the end of the webinar, we'll ask you to complete a very brief survey to give us the feedback that we need to improve our webinars. I'd like to welcome today Neil Mehltretter, Engineering Manager at Kaeser Compressors, and Timothy Hitzges, Product Engineer for Master and Local Controllers at Kaeser. Neil is a Certified Energy Manager, and Timothy is a Certified Project Manager. Timothy, welcome and take it away.
Thank you, Christine. Good afternoon and welcome to today's webinar, Using Predictive Technologies with Compressed Air. Today we will discuss critical and non-critical data, ways to avoid data overload, predictive maintenance, leak detection, lubrication analysis, as well as air quality. The industries today move towards IoT connectivity, and this offers opportunities to better monitor and manage mission-critical equipment such as compressed air systems. Incorporating predictive technologies into day-to-day operation has the potential to improve reliability, increase uptime, reduce maintenance costs. Now, I'd like to highlight some of the key features of smart factories and smart machines, and I want to especially highlight one point here: increased uptime. Now, uptime is essential for lean manufacturing and companies. Any downtime can bring the entire plant or production to a halt. Let's take a look at maintenance models. In the past, strategies were reactive maintenance, and it's fair to say that this is still a strategy today. The current maintenance strategies are towards preventive maintenance. Typical preventive maintenance intervals are, for instance, oil or filter changes. Now, the future is predictive maintenance. The trends are created by analyzing data. Maintenance will be planned in time and before an equipment shuts down. Now let's take a look at the maintenance scenario here. We have two. The one is very well known, a shutdown scenario, and the other one, a failure prediction. Parts have to be shipped. We stay on the left side. Parts have to be shipped and stored. Technician has to be scheduled. Now all this costs downtime. Failure prediction follows a different pattern and does not lead to downtime. And downtime will lead to a chain of action, starting with a customer call and ends with multiple site visits. However, all this results in downtime again and costs money and potential production loss. However, failure prediction starts prior to a shutdown and is based on a real-time data. Parts are available. Service visits can be scheduled in advance before any shutdown occurs. Let's take a look at some data basics. And what we would like to discuss here today is how to differentiate between critical and non-critical data. And let me highlight, critical data are as important as non-critical data. Then we need to understand compressor data. And also, how do we structure an IoT cockpit, but keep it simple. And last but not least, threat analysis and predictive maintenance. Let's start with critical data. Temperature is certainly a critical value in compressor system. And I'll start here with oil temperature. Oil temperature is a good indicator for compressor cooling flow. Running over consistently high temperature can reduce the lifetime of a unit. Air discharge temperature is another critical data point. Higher inlet temperature will significantly increase moisture content and can overwhelm dryers and in return lead to a premature dryer failure. Now let's take a look here at a worst case scenario. Your dryer fails, your required air quality cannot be maintained, and that will lead eventually to a loss of production. Take another look at some critical information that are important to monitor. Motor temperature. Now, similar to oil temperature, is a good indicator for a loss of cooling flow, in particular across motors. Overloading a motor can also be an issue for an increased motor temperature. Pressure beside temperature is another group of critical values and should be monitored in a compressor system. Take a look here at line pressure, or sometimes also at discharge pressure. We compare those to internal pressure, and we see an increase in internal pressure compared to line pressure. Discharge pressure can be a very good indicator for a restriction at discharge. Another value is differential pressure. Increase in differential pressure, and I'm particularly looking here at an oil filter or an inlet filter, is a good gauge for showing if the filter is clogged or contaminated. Furthermore, this can lead to a premature replacement due to a higher ambient contamination. Now here's another very critical information. I highlight that in particular because alarm notifications or alarm in general will shut down a compressor or even prevent a compressor to run. Again, really that highlights how important it is that alarms require immediate attention. And it's good practice to set up an alarm notification pushed down to your mobile devices. Again, alarm can lead to high cost and a delay time. Take a look at air consumption. Now, air consumption is another very important value, and it's not only because we can see the demand downstream or we know the demand downstream. It also identifies leaks and artificial demands, future need for air producers, and also helping to improve a production process. Let's jump over to non-critical information. As I said earlier, they're not less important. Compressor-specific power, or even station-specific power, now that's power consumption per free air delivery, is a benchmark how efficient a station operates. Decrease in specific power or increase in power consumption by stable output, for instance, identifies a restriction at compressor inlet. Controlling a station based on specific power results in higher energy savings, for instance, implementing a higher level controller. Let's take a look at load energy ratio. Load energy ratio considers the total idle energy compared to total load energy. Compressors, as we all know, are most efficient when they are either fully loaded or off. So typically, you want to see a high number for your load energy ratio. Let's take another look at compressor utilization. It's another important value, in particular for multi-unit installations or multi-unit stations with same-sized equipment. The run-hour offset is a benchmark for how well each individual compressor is utilized. For instance, by controlling, again, a compressor station using a higher level controller. Now, compressor cycle time is also a very good gauge and indicator for if you experience frequent compressor cycling, that eventually can result in a wear and tear, and is a good indication, or can be a good indication, to see if your station is well designed or not. Let's take a look at trend analysis. Trend analysis can be basis for predicting future events. And this is a very simple overview, and I would just like to highlight 2 points, as you can see down on the bottom on the slide. Estimating future maintenance, due date based on current and historical data. You see on the left the actual hours, and on the right you see the hours until next maintenance. So that helps you to create a trend. You know when a future maintenance due date is ready or available. Now down the bottom, the second screenshot is compressor utilization based on compressor status information. And certainly, reliable trends cannot be based on a few data points. This requires a lot of data, in fact, a pool of real data. And next, we will take a look at some of the challenges we face today. And a lot of higher level IT security systems are in place, which in contrary can be a challenge to implement a simple but reliable IoT solution within an IoT or an IT architecture. Another challenge are limited signal strength and upload bandwidth at remote locations while using IoT solution via cellular network. Over the years, we experienced a decrease on costs for bandwidth, decrease on costs for storage, and in fact, a lot of algorithms are in place that can sort pools of data to find the right data. Now, does that mean we can stream as much data as possible, as much as we want? Well, too much data leads to data overload, and it is a distraction. More data is not always better. So that poses the question, how to avoid data overload. Let's look at those 4 points here. It's important to have a basic understanding of your asset, and I really want to highlight that. Then the second one, categorize critical and non-critical data. And again, I like to emphasize here, critical are as important as non-critical data. And we've seen some of them previous slides ago. Implementing a good troubleshooting guideline. And in particular, I like to highlight, it's very important to define a problem when you do troubleshooting. And not always isolating each value or data point, just rather look at data in a whole. So now here we look at some data intervals. Data updates per millisecond are most likely not required in the compressed air system, compressed air industry, contrary to some mission critical applications. Second to minute updates are sufficient for compressor critical data, and minute to hour updates are sufficient for compressor non-critical data. Again, both very important data points. I also like to highlight that more sensors are not always better and doesn't add any extra or added benefit to an operator. Let's take a look here at an IoT cockpit, and this is really an example. IoT cockpits should not be limited to web browsers. Rather, it should be accessible via mobile app or with push notification. And I would like to add, should be available for tablets as well. It's good practice to have a geomap for different locations. Also, use a color code for station health status. That helps with an overview. And good practice is to have red for alarms, orange or yellow for maintenance, and green for status is fine or status okay. Also, group critical data together in one overview. Just Take, for example, line discharge pressure or oil discharge pressure compared to temperature. And also here on the pictures, you see on the left bottom, display important compressor status information, or displayed important compressor status information. I'd like to highlight load and idle. Keep an eye on that one as well. And list all current alarm message. I also recommend list all messages. It helps with troubleshooting and gives you a very good overview. Compressed air systems are quite often integrated to higher level controls or industrial automation system or even building automation system. And industrial gateways, as we can see here in the picture, enable a compressor to communicate via industrial protocol and can be basis for an IoT solution as well. Nowadays, there are quite a number of IoT gateways available on the market. I'd just like to highlight here Ethernet IP and Modbus TCP, which are very common on the US market and in our industry as well. So here's an example for a low-cost application or low-cost IoT solution, and it's a very generic overview. However, certainly sufficient if you are interested in just a limited amount of data. Let's kind of go through this example here. So we have on our right a data process map. You would eventually select your important data points. And I selected Modbus TCP. Modbus itself is a very simple, lightweight protocol. There's a lot of free tools available to implement Modbus TCP. Then if we go over to the left, low-cost IoT or IoT gateways are available as well that communicate from Modbus to Modbus TCP. I'd just like to highlight here a single-board microprocessor, and you're probably aware of Raspberry Pis that support Wi-Fi or a local area network. Now, you need actually to create a secure channel. I highlight or recommend MQTTS, which is a lightweight message protocol, to communicate to a database, which you can use a cloud database or even a local database works as well, and use APIs to subscribe or publish data from your desktop app or mobile device to your smart device, which is an IoT gateway. So on the next slide, you see there's an example for collecting more data points. And that certainly makes sense if you have bigger stations and you're looking for a fully integration. So a higher level control or an industrial automation system is certainly more appropriate for those large amount of data. And most common higher level controller or even PLCs or SCADA systems have onboard storage or even use storage in a cloud. And modern air producers support industrial Ethernet, which simplifies data collection. Let's take a look here at streaming data. The data that you collect, we see in the previous slide, that will now be pushed through a secure network to a cloud or data server. And the IoT cockpit can now subscribe to a cloud or server to receive real-time data. Good IoT cockpits allow users to not only display everything, also to build the individual charts and graphs, subscribe to individual data points for different applications. I think here about technicians or product monitoring, or just in general to have an updated report for an operator. And not to forget, create reporting. Finally, we have our predictive maintenance. And here's an example for predictive maintenance, predicting future temperature trends, as you can see on this graph, to detect abnormalities based on algorithms and on IoT architecture that we just looked at. Now, all this enables an operator to schedule custom specific maintenance visits. So therefore, we can say that algorithms are substantial to help sort through a pool of data, simulate different scenarios based on a digital twin, and piece the right trends together to predict future events. Neil Mehltretter will now show us additional ways to proactively monitor your system.
Thank you, Timothy, for giving us a great overview on what we can expect to see in the near term regarding gathering and using data from industrial machinery. Now I'd like to talk about how many plants are employing proactive techniques to improve compressed air system reliability and efficiency. There are several ways where operators can gather and use information to reduce costs even before they work out how to employ IoT for better asset management. There are readily available tools that, unfortunately, too few plants are taking full advantage of. Compressed air systems evolve over time, and the best way to shepherd your system to a long lifetime is to monitor it. Timothy highlighted onboard data trends, but there are a few that should be considered either in addition to or in conjunction with this data collection. Specifically, ultrasonic leak detection, air quality, and lubricant analysis. Most industrial equipment already has sensors installed and can be used to bus to other networks, but these are pieces that are different. And I want to mention that after the webinar, all attendees are going to get an email to download some of our technical white papers, including one on leak detection as well as lubricant analysis. So if you're interested in diving deeper into these topics, I suggest both of these as an additional resource. Leaks in your compressed air can cause drops in system pressure, compressor cycling for no reason, shorter lifetime for system components, and they can require additional compressors more than you really expect. All of these things are going to increase production and maintenance cost for your compressed air system. The topics highlighted herein are what we're going to talk about in the next few slides. Review the information for trends and analysis. The goal of your system should be to maintain leaks less than 10% of overall production. However, normal leak load is between 25 and 30%, and we've seen it much higher. Plus, the inappropriate uses and artificial demand brings the amount of useful compressed air down to 45 to 60% of production. Anything you can do to put this compressed air back to an efficient use by reducing or eliminating leaks, inappropriate uses, and artificial demand will go a long way to the overall bottom line of your compressed air system. You know, leaks are going to occur over time. The type of piping material, the age of your facility, the size of the facility, all of these things are going to influence the number of leaks you're going to see. Facilities that have only one compressor may only need to check for leaks every year, but it really depends on the size of that compressor as well. If during that one check, the leak load percentage is found to be over the expectations, say significant, maybe 30%, then it'd be recommended to repair the largest leaks immediately and perhaps check the leak load again in a few months. If the facility is large, then it might be beneficial to perform a leak audit once per quarter. Additionally, the cost of compressed air is going to differ from location to location. However, again, with larger facilities, the cost of compressed air can skyrocket. Therefore, a quarterly leak audit might really be worthwhile. Let's take a broad view of what the average system is losing to leaks. So what you see on the right-hand side of your screen is what we're going to talk about next. Of course, the numbers up here are averages, and they may be significantly higher than your particular system, but they give you a general idea of what money a plant could be losing to leaks based on how large its compressed air demand actually is. The values you see here are based on 24/7, 365 days a year at 7 cents a kilowatt hour and 100 psi, as well as a 25% leak rate. So, just a ballpark number is pretty flabbergasting. Bottom line is, this is money that's directly in front of you, and it's ready to be added back to your bottom line. So let's talk about how we can fix some of these leaks. There are three types of leak detection that you'll normally see. First is that listen and feel. These can be found doing a general walkthrough of your facility. If you have a shutdown period where compressed air is online, but normal production is not, you might be able to hear the hissing sound of your leaks and also the wasted energy that's going out with them. This is a great time to tag the leaks and then repair the leaks when the system's depressurized. Don't lose momentum. Otherwise, as we've seen in many plants, these tags can stay on indefinitely and the leaks continue to waste energy. The soapy water test, that can be done at any time. Usually it just means you have to be able to get access to those joints, and this would be recommended within a compressor room, and is typically done to test a system at startup or whenever maintenance, repair, or additions are made. Lastly, we have that ultrasonic, and really this is the industry standard. While it does have specialized equipment and requires training, it's fast and accurate and requires no plant downtime to check or physical contact with the leak for the operator. Ultrasonic leak detection, like I said, requires specialized equipment. You can see an image there on the right, and you can see the tag underneath it. But they do have distinct advantages. It can be done from a distance. You can discern the leaks in a noisy environment. And it's also going to give you an estimate of the volume for that leak. And this can help you prioritize which leaks to fix first. Many compressor vendors offer this service, or you can rent the equipment. The first time you're doing a leak audit, I'd recommend hiring an experienced professional to do the leak audit for you, and then really watch and learn and determine if that's something your facility wants to do on their own. As Timothy showed us, trending data can be easy to do, but it may not be easy to analyze. A quick tip would be to pull up, if you have this kind of data, pull up your flow values for the weekend or holiday operation. Check what percentage of your flow is running during this period, and then trend that information. Has it gone up or down? If the change is significant, address it immediately, either with another leak audit to find and fix those leaks, or maybe with a company-wide announcement on how much you've reduced your leaks. There's plenty of incentive to empower your personnel. A quick anecdote, when we were touring facility with maintenance personnel, we found a quarter-inch ball valve on a large receiver that was wide open. When we asked the maintenance person, he said, yeah, we leave it open all the time. And we asked why. They astutely said that the tank had entrained a lot of water, which passed downstream and led to product scrap. So we asked what their limit was for a purchase order, and they said something like $500. When we told them that this particular leak on this particular ball valve was costing the plant upward of $10,000 per year, they quickly purchased a no-loss demand drain. When designing plant air systems, people have different expressions to indicate the overall level of air quality needed. We hear shop air, plant air, CDA, or clean dry air. We hear instrument air, and these are commonly understood, but they're not really well defined. Instrument air really is a classic example, and many think it requires a desiccant dryer, but it's not necessarily the case. It really depends on ambient conditions. ISA S7.3 describes instrument air in terms of system design and specifications, but it's still rather broad as it doesn't prescribe specific levels of air quality. Further, it specifies that pressure dew point must be 18 degrees Fahrenheit below the lowest ambient temperature. Particulate must be less than 40 microns, and that oil concentration must be less than 1 part per million. So, the ISA standard also notes that air quality must meet the requirements of the user. So the burden then ends up falling on the user to understand and be aware of the requirements needed for their particular application. And so with that being said, let's look at what we can do. Even after you've decided on what your air quality requirement is, there's a maintenance factor that you must consider. Equipment's typically in its best condition, hopefully that's the case, when it arrives to your facility. After the equipment's in operation, there's going to be wear and tear to consider. Heat load in the compressor room, moisture content in the air, dust and dirty environments, all of these can increase wear on your compressed air system. Therefore, to ensure that all of your equipment is running optimally, service is going to be recommended based on prescribed intervals. But you also may need to adjust those intervals based on site-specific conditions. Compressors, dryers, and filtration, usually these are the main focus of service. However, don't neglect your drains or your condensate management system. These could be your weakest link in the system. For example, if a drain fails, water can be entrained in your air system, which can then be pushed to the point of use, creating significant scrap or rework rates. There's a set of specifications for compressed air quality. So ISO 8573-1, 2010, it sets classes for specific levels of particulate water and oil. Specifying the ISO level for each contaminant based on the requirement of the application is going to provide usable guidelines for selecting your air dryers and filters and or figuring out what you actually have at the facility. If you take the specific level from each of those three categories to give the ISO class, so in this case what we're seeing here is ISO class 1.1.1, which would be class 1 for particulates, class 1 for water, and then class 1 for oil. And like I said, this will give you a baseline of what the air treatment system is supposed to provide for you. And over time, like with other data points, you can actually trend the air quality. Most facilities would consider pressure dew point the staple of an air quality measurement. After all, moisture in your product line could result in a plant stoppage and potentially millions of dollars worth of product scrap. Dew point monitors are readily available as off-the-shelf items and can be added to any compressor station, either to send as a 4 to 20 milliamp signal to your plant control system or via a master controller. Alarms and warnings can then be sent to ensure that the plant addresses the issue. So that could be a high alarm or a high alarm. So, maybe a warning first and then an alarm second. What they do with the alarm, that depends on what the critical nature of your business is. If it's a warning, perhaps it does nothing. If it's an alarm, perhaps it shuts the station down or closes a valve. So particulate and oil measurements, those are more difficult, but there are devices out there that can help you trend the data. But just be careful, as in order to get that kind of resolution, especially on particulates, you need high-quality devices, which are expensive to install. And for oil concentration, really, sampling can be done periodically and evaluated by a reputable third party to figure out your trends. All manufacturers provide a recommendation for frequency of oil analysis. Be aware that standard recommendations are not necessarily what the plant should adopt. And like we've mentioned before, if you have a dirty, dusty, high-temperature environment, then more frequent oil sampling would be recommended. Also, the type of lubricant, such as mineral oil or food-grade oil, will play a role. Other things to consider are what's required at each sampling interval. The load and service hours of the compressor, along with the lubrication hours, are key. Another imperative is to get a clean sample. And as I just mentioned, compressor rooms and therefore the compressor itself aren't always the cleanest environments. If there's particulate on the oil drain, then those particulates are going to contaminate your sample. So getting a clean sample is going to help you with your trend analysis, no question. Items to look for when you're taking a sample would be water, metals, and varnish. The pictures here show instances where failures have occurred. You won't be able to see this kind of definition per se with just a sample, but you'll see these images, with these images you're going to see the effects. Without proper lubrication, there's going to be failures. The point of the oil sample would be to help determine these issues prior to a failure. If you do find these issues in your oil sample, there are a few things that you can do to determine if the issue requires immediate action. Check with your supplier prior to your sampling, or if your supplier is doing your sampling, they're going to know how to handle the situation if it arises. Here are two sample reports. The one on the left shows an oil sample that's passed inspection, whereas the sample on the right shows that the oil is operating in a severe condition in regard to particulate contamination. The particulate count's high, along with the oil cleanliness not being sufficient. So having this trend analysis helps to determine the condition of your equipment, and if the situation is a known problem, helps you figure out how to address those issues as you move into the future. Like all items, all the other items that we discussed, determining a schedule and review that schedule regularly. If there are problems, discuss them with your service providers. If you have a hot, humid, dirty, and dusty environment, then samples should be taken more frequently. Be proactive. Don't shy away from any of these types of analysis, but keep in mind that operating conditions in your compressor room are going to have a direct effect on the reliability of your compressor. Just because you're streaming data doesn't mean, now I don't need to go out there and check out in the compressor room. The data is going to help you figure out your trends, but when you walk into a compressor room, you can tell if there are going to be issues or not based on the environment, based on the condition of the equipment. The items listed above, they're going to ensure that you've got a reliable and efficient system to start with. So locate your compressor inlet near clean, dry air. For water-cooled machines, you want to provide clean, cool input. You want to stop the compressor regularly to remove water in the separator. Also, you want to make sure you have a clean inlet filter. And like we talked about, change the lubricant before it gets beyond its useful life. The last point here is properly apply the compressor. I can't stress that enough. Typically we see a lot of undersized machines, or your plant might be a system oversized, or where the compressor duty cycle is very low, like Tim mentioned. Other items to consider would be bearing life, which is directly affected by operating conditions, the environment, as well as duty cycle. So one thing that you can consider would also be vibration analysis, which would require a baseline prior to startup, and then can be monitored continuously or via discrete points in time. To summarize here, there's a multitude of data points that you can collect to better monitor and manage your compressed air system to help improve reliability, increase your uptime, and reduce maintenance costs, as well as increase the energy efficiency of your system. Understanding what points are critical to your operation and which are highly useful but not critical is a big step in effectively monitoring, tracking, and analyzing your compressed air system data. This will also help you avoid data overload. Remember that non-critical data is still important, but that you might not review them as often as critical data. Take a look at your current system. What are the possibilities? And what are the requirements? What are your obstacles? What are the next steps for the plant? And how can you get ready? We'll give you a hint. Look at the communication capabilities and the equipment you already own and start using it. With some advanced IoT capabilities that present challenges, there are simple ways to proactively improve your compressed air performance with today's technologies. Comprehensive leak detection program, regularly scheduled lubrication analysis, and efficient air quality components in your compressed air system, they're going to have a big impact on your system's operation. We see real improvements in life cycle cost reduction as well as asset management in those plants who employ proactive technologies. I want to thank everybody for joining us today, and I believe now we have some time for questions, so I'm going to send it back to Christine.
Yes, we do indeed, Neil. Thanks very much. Thank you to you and to Timothy. That's really just chock full of great best practices and strategies. Such important points about data collection, and it can be such a challenge, but it's so critical to get the right data to the right people and display it in the right way to extract meaning from it. And the points too about the compelling savings that you can get from just fixing your leaks, and the fact that it doesn't have to be this behemoth thing, that there are these simple things, simple steps you can take to really make a difference. It's really powerful. We'll go ahead and turn now to our Q&A. Looks like we have a question here. what's the best interval for taking a compressor oil analysis sample?
Yeah, that's a great question. I'm going to have to kind of defer a little bit. It depends. Usually you want to take an oil sample right away after the first run, or maybe a few weeks to get yourself a good baseline. In my opinion. And then you want to take a look at maybe 2,000 hours, or depending on when your service intervals are going to be. The idea is that perhaps you don't want to take the samples too often, but if you're going to have a run time and a change, you want to make sure that you're getting a sample in between that. So, and again, it also depends on after you've got your first run in and your first oil change. Do you do it yearly? Do you do it more frequently? And it depends on the severe condition, let's say, of your first report. So it's going to be variable, but it's a good question, and it really depends on your current environment. So.
Okay. Beyond oil analysis, but related, what are some other tips you'd offer for collecting data, between or before doing a trend analysis?
Take a stab at that, Tim. So the question here, how long do you recommend collecting data before doing a trend analysis? It really depends. I mean, typically you're looking at data over a longer term period. So from a trend analysis, you could have a trend analysis based on 2 weeks worth of data, but it does depend on how the plant operates. So if your plant's seasonal or cyclical, or you just landed a huge contract, things are going to change regularly, let's say. So, from my opinion, like I said, you could trend data from a 2-week interval or maybe even less. And some plants are very stable. Maybe you have 1 hour worth of data, and that's sufficient to make a determination for everything else. But, in actuality, I'd say usually 2 weeks is probably a decent sample. But from a trend analysis, I kind of mentioned this too when we were looking at leaks. You can look at a flow profile over the course of time and then figure out how your leaks have changed, and also what your baseline flows are. So, and the only way to really do that is if you have more data. So, from a certain standpoint, if you look at seasonally, you say, well, December is our highest month and March maybe is our lowest month. So if you have a 3-month interval there, that might be a great opportunity for you to figure out, okay, how do your temperatures run? How does your flow perform? What's your leak load during, federal holidays and that kind of thing? And then, getting back to temperature analysis on machines, your room might be very cold, the compressor room in the winter. And in that case, your temperatures are going to be relatively low compared to summer months when, if we're talking unconditioned spaces, then your compressors run very hot. So, from that standpoint, you might need to have seasonal information or trends over a year to figure those kind of things out.
Okay. We have a question next on leak detection. Do you recommend investing in leak detection equipment, or should a company should we outsource the task? That's a tough question to answer. Some people feel like they want to do everything, and some people feel like they want to outsource some of these maybe not necessarily critical pieces, but smaller tasks. So it depends on the company that you have. If you have small resources, you have a very small maintenance staff, they're always busy, then I would say I would definitely contract that out. If you have a large maintenance staff and you have a large facility, and it's something like I talked about, maybe you're doing quarterly assessments on your leak detection, then I'd say it would make a lot of sense for you to invest in some equipment, invest in some training, and do it yourself. So it does run the gambit, but there's a lot of companies that are out there, very reputable firms, that this is what they do all day, every day. So in a lot of cases, it does make sense to outsource. Okay, great. Our next question, we use food-grade lubricant in our equipment. Should we check it more frequently?
Like I said, it depends on your environment. If you have a high dust, dirt environment, then I'd say probably. If the trend analysis shows after the first few checks that you're in more of a concern condition, I wouldn't necessarily say severe, then I'd say maybe you would want to do that more frequently. But in general, I would probably just follow the recommendations of your manufacturer.
Okay. Here's a loaded one. What's the most important data point?
I'm going to let Tim answer that because he's shaking his head like I can't answer that.
So I have to smile a little bit because there's not only one important data point. There are a few, in particular, compressor application or compressor environment. Pressure and temperature are the two main values. If you really want to narrow it down and you have to sacrifice data points, then that's certainly something you want to look at in a direction. But again, it's not necessarily that there's one important data point. It's always a combination of data that you need.
Right. Okay. And then finally, it's like a question specific to Kaeser. Do you guys offer a construction inspection to ensure that units are installed according to Kaeser's specifications?
That's a good question. Typically, this is a Kaeser-specific question. I'll just kind of generalize it. This is Neil again. When someone comes out from a startup standpoint to start up a piece of equipment, whether it be a rotary screw compressor, whether it be a dryer, whether it be another piece of operational equipment, there's going to be checklists that we're going to go through, or the installer is going to go through to make sure that the system meets the needs of the equipment. And typically that's service-related dimensions. It's typically electrical as well. It might even be a safety situation where maybe the compressor is in a very small space, and from an access standpoint, if we were servicing equipment or someone else was servicing equipment, could they be able to get out easily?
Right. Sure.
Other things that we would look at certainly would be headers, would be size. We talked about leaks. We talked a little bit, maybe mentioned restrictions. For example, compressor discharge. Let's say the compressor discharge is 1.5 inch MPT connection. Usually, rule of thumb, we would say, okay, go up to the next half size up, which would be 2 inch. Not to say that system headers aren't 1 inch or maybe smaller. So those things would be restrictions, and regardless of which color package you put in, whether it be yellow or gray or what have you, you're going to have a problem. So those are things that seasoned installers, technicians, they're going to see, they're going to identify. In regard to headers, this was something that we didn't put in the program today, but you want to make sure that you have a flexible connection. You don't want to have in-train water from one compressor get to another, so you want to gooseneck that pipe, down into a main header. You want to make sure that the piping's secured to a wall or to maybe even the ground. So there's a bunch of different things that I would say a seasoned technician or an installer is going to look at and say, these are the 7 things that we need to change. These are the 10 things that are questionable, but you can get away with it. And it's also electrical. So there's a lot of things to look at, and highly recommended to have somebody who's knowledgeable about your equipment, whether it be compressors or something else, to be there at a startup.
Yeah, critical point. If you're going to install it, it's got to be the right way and to have it working right. That wraps up our Q&A portion. So I'd like to again thank our speakers, Neil Mehltretter and Timothy Hitzges, our sponsor, Kaeser Compressors, and all of you who joined us today. We want to remind you this webinar has been recorded and it'll be available shortly for on-demand viewing. You're also encouraged to visit plantservices.com to gain access to even more tools and resources aimed at helping you achieve success. The full set of speaker slides from today's presentation will remain available for on-demand viewers in the handouts area. And then finally, we want to know, did you like this presentation? Let us know your thoughts by answering our brief survey that will appear on your screen shortly. Your candid answers are not only appreciated, but also they help us craft future events. So thanks again for your attendance, and have a great rest of your day.